And so instead of fancy PowerPoint, this is just a paper that Victoria White and I are working on. This is something that I've been teaching in PChem 1, or PChem 2, sorry, thermodynamics for a while. I just, on a lark, wanted to see if this would work. You know, if I could just come up with a quantitative structure property relationship, which we'll discuss what that means, for molar volume. Because as you saw, perhaps, on the previous exam, that sometimes you've got the substance, but you don't know the molar volume. And I mean, you may, certainly if you know the molar mass, which you can calculate from the types of atoms, but what about the density? You know, if you have the density, then you can get the molar volume. But if you don't know the density, you know, then what are you going to do? And so I thought, well, it makes sense that if I've got more atoms, I ought to have a bigger molecule. And so I just took the density of a bunch of molecules and the molar mass of a bunch of molecules and tried to do a linear fit, a regression, to see if I could get the molar volume from the molecular formula. And it worked. It does pretty well. And so that's what we're going to do today. And this is a great introduction to these techniques that we have called quantitative structure property relationships. So you have a structure, and that structure can be pretty complex, like a protein, you know, with certain R groups. And if you know the types of R groups and so on, you might be able to come up with a property relationship. So you have the structure, the different R groups and amino acids that are involved, and then you have a property that you're after. And you can just do a linear regression to match the structural properties to the structural elements to the properties that you're after. So it's a statistical approach. It's pretty easy in terms of math. I mean, we have software that does these things for us. And so let's walk through this. There's a literature review in this paper. Again, I leave it to you to enjoy that on your own. But let's get down here to the actual method. I mean, you've already been doing quantitative structure property relationships since your freshman year, or even your high school days in chemistry. So you are given the molecular formula CH4, and you're asked, what's the molar mass? Well, the structure is CH4. It's 1 carbon and 4 hydrogens. And you have a relationship known as the periodic table. So you go to the periodic table and you pull the masses for carbon and hydrogen, and you take the structure and you turn it into a property. That's all you're doing. And we do this very simply with mathematics using this matrix formulation. So the S here is the structure matrix. It's certain numbers that are associated with the structure. And in our example for CH4, it's the carbon and the number and types of atoms. So carbon would be A, it would be 1 carbon, 4 for the number of hydrogens, 0 for nitrogen, 0 for oxygen. And so we would have this structure matrix, 1, 4, 0, 0. And then we would have a property matrix. And the reason they're written funny is this is matrix multiplication. We take the row times the column and add all the elements. So we multiply and then add. It's the sum product. So you take this here, you multiply every element by every element, and then you add up the results, and we get our property. So this R piece here is the relationship matrix. So these are the terms. You have the structure matrix, and you have the relationship matrix, and you get the property value out. And this is quantitative. So that's what QSPR stands for. It's a quantitative structure property relationship. So if we know the structure and we know the property, we can do statistics to find the relationship matrix that maps the structural matrix into the property that we're after. Can I get a show of hands of who's had or is comfortable with linear algebra and matrix formulations? So, okay, that's fine. I expected it to be an introduction into matrix multiplication. So, you know, if everybody raised their hand, I would go a little faster. Okay, so we'll go nice and slow through this. But is anybody confused about this matrix formulation? We've got this row, and we're multiplying by a column. So we kind of tilt that row up, and A is multiplied by RA. And that's it. It's not multiplied by RB or RC. It's only multiplied by RA. And then B is multiplied by RB. and C is multiplied by RC, and then we add all those products together to get M, our molar mass. Okay. And so let's do that. Let's go to the spreadsheet. And if you should download this training set spreadsheet. And I've gone to the CRC and I've pulled down 120 compounds. Oops. So we've got all kinds of different molecules here. I wanted to get a variety of molecules, so I have some organic acids, alcohols, anhydrides, esters, isoparaffins, nitriles, nitros and nitrates. Paraffins were just saturated, alkanes and so on. So I wanted a variety of types of molecules because I didn't want my relationship matrix to be only one type of molecule. I mean, that's what Hildebrand fell into. His work was with alkanes. And so then when he started looking at alcohols and things, he didn't have a hydrogen bonding component. And so it really didn't work for his solubility studies. So what we've got is, we've got this molecular weight formula here, and we've got the molar masses from the periodic table. Notice this intercept value here. Let me talk about that for a little bit. And we've got this intercept column of ones. For molar mass, we don't really need that because if you have 0 atoms, you have 0 mass. Make sense? But for other properties, it may not go through 0. Just statistically, it may not go through 0. And so we'll find later on when we do molar volume or when we do heating value, combustion enthalpy, that we'll need that intercept term. So we have this column of ones, which sort of takes into account the intercept. When we do matrix multiplication, we're going to need that column if we have an intercept. So let's look at our formula here for molar mass. I'm going to make it big here. And so look how we can do this matrix multiplication in Excel. It's the mmult function, and we have a block of data. So we have mmult, and then you give it the initial block of data. And so this is all of 120 rows. We have 110 compounds. And then we have that multiplied by our relationship matrix. So this is the molar mass of carbon, the molar mass of hydrogen, nitrogen, and oxygen. Does everybody see now if I have 3 carbons, 2 hydrogens, and 2 oxygens, that those are going to be multiplied by their respective numbers and added together, and that's going to give me the molar mass. Now the way we enter these formulas, let me just show you that. We select the whole, let me go ahead and delete everything below here. Okay, let me delete everything. So the way we enter this formula, we say, we select the whole area. Sorry, that's going to be a problem. So we select that whole area that we want to fill with that formula. It's called an array formula. And whenever you're dealing with mmult, it's an array formula. It's going to generate a whole array of values. And so you have to select the whole array that you're going to fill. And we come up here and type in equals mmult, open parenthesis, and then we select the full array of values. These are the structure, this is the structure matrix. And then we hit comma, and then we come up here and select the relationship matrix. And we're going to go ahead just for grins and anchor that. So hit F4 to put $signs in front of the rows and columns. Close parenthesis, and then this is the real trick. You don't just hit enter, you have to hit Control-Shift-Enter because it's an array formula. And when you hit Control-Shift-Enter, it copies that value all the way down. And that's the thing that most people mistake with doing array formulas is Control-Shift-Enter. So I hit Control-Shift-Enter, and I've done a 110 matrix multiplications. And this gives us the molar mass for all of these compounds. Now this is also a very handy tool and this is part of your portfolio, your Excel portfolio, is now we have a little tool where you can type in the molecular formula for any substance and get its molar mass, as long as it's CHN and O. Okay. You could expand this yourself to include chlorine and bromine and whatever is in, rubidium or whatever it is that you've got in your molecules. But at this point, we just have CHNO. So I would suggest that this would be one of the tools for your Excel portfolio, is just to make a molar mass calculator. It's not necessary really for small molecules, but some of you have some pretty big molecules. If you do mass spec, you're going to want one of those, right? Because you're fragments, and you're going to want to quickly determine, okay, what fragment will give me this mass that I'm detecting, this M over Z value. And so one of these little calculators is pretty handy, and that's a great use for Excel. So we have our molar mass. Now this is what I would call the literature value, because this is using the data from the periodic table. Okay, so that I would consider that literature, okay, in this situation. So these would be the accepted or exact masses for these molecules. Again, it's the average, isotopic averages, so they're taking into account the relative abundance of carbon-13 and so on. Okay, question? Okay. Is everybody with me so far? Okay. Let's pretend we don't have the periodic table. Okay. Let's use this training set. Let's say we've got this list of molar masses, but we don't have the carbon mass or the hydrogen mass or the nitrogen mass or the oxygen mass. So somehow scientists working diligently in the lab have determined the molar masses for these 110 compounds, and we want to know what the mass of carbon is. Just carbon. And the mass of hydrogen. We have the property, molar mass, and we have the structure, but we don't have the relationship matrix. So we could do a linear regression. Okay, so let's do that. We're going to create our own QSPR over here for molar mass. See over here this relationship matrix? We're going to determine the mass of carbon, hydrogen, nitrogen, and oxygen using this data. So what we do is we come up to the data ribbon, do data analysis, and scroll down a little bit to see the regression item. Pick regression. Is everybody following along? Okay. Hit OK, and then we get the regression dialog box. Okay, so the Y range. The Y range are the dependent variables. The dependent variables are your properties. So we want the property of molar mass to be our Y range. And so we come down here and pick the literature values for molar mass. So it should be H10 through H120. Okay, so we got column H, H10 through 120 for the molar mass. And then for the X range, these are the structural variables. So this is the structural matrix, and we want carbon. Oh, let's do this. Let's get labels on this. So come back up to the Y range, delete what you've got, okay, and grab that title too. So molecular weight, and go all the way down. So we're going from H9 to H120. See, I've got the molecular weight here. And then I'm going to click this checkbox label. See here, label, this checkbox? Click that to tell it I've got a row of labels in my data set. Okay. This will be helpful because later on when we get the structure matrix, we'll see CHNO in our regression output. And so then in the input X range, we're going to grab the carbon, hydrogen, nitrogen, oxygen labels and go all the way down. And so we're going from D9 to G120. So it's going over 4 rows and down 120 rows. So let me go back to the top. You can see what I had selected. Okay, never mind. And so I'm going to call that worksheet ply MW1. MW1. And for educational purposes, I want to make sure that you do not have this constant is zero checked. This constant is zero should be unchecked. So it's going to solve for an intercept. Okay? Is everybody good with me so far? All right, then we can see, okay. And it produces this regression output. Now here's my trick in terms of auto-scaling everything. I select all of it and double-click that divider between A and B, and it auto-scales everything. And I have an intercept, and then I have the molar mass of carbon, hydrogen, nitrogen, and oxygen. It's pretty darn good. Okay. In fact, it's way better than what I had before because I had a miss, like one of the numbers was mistyped, but this nailed it. Okay. Yeah, so look at the p-value for the intercept. Okay. Did you watch the video? I know y'all were on travel for the regression output. What is the p-value telling me? Yeah, so that's technically what it is. It's the probability that the null hypothesis is true. So someone else interpret what Jerome just said. What's the null hypothesis? Yeah, so the uncertainty in the data does what? Yeah, so this uncertainty in the data gave us that intercept. It's p-values. The null hypothesis is that uncertainty or variability or noise in the data gave us this intercept. So that's the null hypothesis. And the intercept is 3 times 10 to the minus 15. Okay, very tiny number. And the probability, the p-value is the probability that noise gave us that number. Yeah, it's 50-50 chance. Yeah. Right? And so we want a p-value less than 5%. We want it less than 0.05 for us to have 95% confidence. Here we're less than 50% confidence in that number. Okay. So what we're going to do is redo the regression, and we're going to check that box that says intercept is 0. So a lot of times Excel remembers your settings, and so you go back to data analysis, hit regression, everything looks the same, but just click constant is 0. And this just tells it to say, hey, if, oops, I messed up because I didn't change the name of the regression. So I'm going to call it MW2. And so that's pretty amazing that we have 0 p-values, and we've nailed the masses of carbon, nitrogen, hydrogen, and oxygen.
We are checking that later.
We are checking it for the second regression. Yeah, so we check it and say the constant is 0. Don't fit a constant. And so then it only fits the coefficients in front of each column. Any questions so far? This is the simplest QSPR that you've ever done because you do this all the time, right? You take the number and types of atoms, multiply by their molar masses, and you get the molar weight. Okay. Now let's do one that's more interesting. Let's do the molar volume. So I also, from the literature, pulled out the densities of these substances and then computed the molar volume. And you can see it's just the molar mass divided by the molar volume. And so the per mil comes up on top. So we have mils per mole. Okay? And so the theory is that, if you have a larger number of atoms, more carbon atoms, the molecule ought to be bigger. It ought to take up more space, so it'd have a larger molar volume. So now let's take our our regression analysis. We're going to select with the molar volume label all of these values. So now we're going J9 down to J120. And I'm not going to put that constant 0. So I'm going to uncheck that constant 0 box. And our structure matrix is still D9 through G120. So we don't change that. We still have carbon, hydrogen, nitrogen, and oxygen labels, and it goes down to the bottom. I'm going to call this MV1 or VM1, VM1 for the regression. And I'm going to hit OK.
What was it for the oxygen?
The X was, let me go back. The X was going to be the J column. So J9 through J120. No, the X, that was the Y values. The X values were CHNO. Yeah. Yeah, and then all the way down. Okay, so we now have this. Yeah, let's make sure everybody's done with the regression. So wait till everybody gets to this point. Let me make it a little bigger so that you can actually see the numbers. How do we know if it's pretty good? Well, we've got a decent R squared. We got 0.97 for an R squared value on 110 compounds and different types of compounds. We have some nitrates and we have some amines and nitriles and so on. Aldehydes, ketones, alcohols. And look at our p-values here. Yeah, they're pretty good. They're, we have our standard errors and our coefficients. So what's the issue? I can help too, maybe. Okay, control shift enter, so you get all of those. Yeah, that's just one way to do it. Yeah. I'll wait till everybody gets to this page. While we're waiting, any questions from others? Did y'all get to this part? You have the VM.
How
Yes.
do we select entire column when we increase X and Y?
Okay, let me show you. Okay, so the question is, let me tell you exactly what I'm doing when I select all of my columns. So I come up, I hit data analysis, and I do regression, and I have this input Y range. I click here, okay, and then I hold Control, Shift, and down arrow. So the Control down arrow goes to the bottom. If I hold Shift down 2, it will select. So Control down goes down, Control up goes all the way to the top, but if you hold Shift down, it selects while it's doing that. So I click the top cell, hit Control Shift, and then hit down arrow, and it'll zoom to the bottom, and then I let go of everything and click a different place in the dialog box. Yeah. Yes, and so that's another thing. If you wanted to look this up online, type in hotkeys for Excel. Yeah, so hotkeys for Excel will give you all kinds of things. Yeah. Pardon? You can click and drag, and we only have 110 rows here, but sometimes that's not convenient. If you have 2,000 or 2,500 or something, it's just, you're wasting a lot of time dragging. Yeah. In fact, I've had data so long that if I try to drag, by the time I get to the bottom, I will have forgotten what I'm doing. So the mean time between forgotten memories and the length it takes to drag to the bottom is a competition for me. So yeah. So and then the same thing for the 4 structure columns. If I click this carbon here, let me delete everything in this dialog box. So I've got the cursor here. I click the carbon. I hold Control Shift right arrow. Oh no. So Control Shift, and I don't use the control. Okay, let me start over. Let me delete everything in that dialog box. Okay, so I click where I want to go, hold Shift only, Shift to the right, 1, 2, 3, hold Control down, and go to the bottom. Okay, and then I've got it. So then, again, these little hotkeys save an enormous amount of time. Yeah, but if it does something wrong, just, panic and bail out like I did. Okay. Yeah, and so then I've typed in VM1 for the new worksheet and then went, okay. So we'll cancel that and cancel that because we already have it. So everybody should be to this regression here. We've got the R squared value, which is great, okay. We've got the coefficients. We have a non-zero intercept, and so now I'm going to show you how to take that into account with our modeled values. And then we have the standard errors in these too. So we could do propagation of uncertainty with our results. We're not going to do that today, but we could if we wanted to. Okay. So what I want to do is I want to take these coefficients, just select these 5 coefficient numbers and copy them. So everybody grab those 5 numbers and hit Control-C for copy. And then I'm going to come back over here. The way I've constructed this spreadsheet for you, I've got a place for this. So we're going to come over here to the VM relationship matrix, and I'm going to paste them right here. Intercept, CHNO. Okay, so we have those 4. That's my relationship matrix. Now don't be confused, it's just a column matrix. It's one column, but it's still a matrix of numbers. And then right here, we're going to do that QSPR. We're going to use our relationship matrix to calculate our molar volumes. And we're going to see how good they are. Okay. So somehow I need to select all the way down to the bottom. Now here's where, this is a weird Excel trick. Okay. Bear with me. All right. If I try to use control down, look at how many rows it goes. It goes down to 1,048,000 blah, blah, blah. So that's a problem. I can't use my little control hotkey if there's no data there. The control goes to the end of the data. So we're going to go around the horn. You know this phrase? Go around the Horn of Africa, instead of cutting through, a land route or maybe the Suez Canal, you go around the bottom. So we're going to go left where I do have some data. So watch this. I go left, 1, 2, 3, where there is data. Control down, now I'm at the bottom. And I go right, 1, 2, 3, and then Control Shift up. Okay, but I don't want to use that molar volume line, so I'm going to go down one arrow, down just with the shift, down one arrow. I didn't use the shift. Okay, so now I've got the data column I collected. Now that's an unnecessary trick, but I use it. Okay. I want my little box to be in the top though, and my box is at the bottom. The little clear box where I can type in the formula, now it's at the bottom. And so just hit tab one time. So it's at the bottom and you hit tab and it goes, whoop, it wraps back to the top. If you just keep hitting tab, it goes to the next deal. So you can go round and round and round until you get sick. Okay, yeah. I've gone too far. I'm going to shift tab and go backwards. Yeah. Oops, I went too far. Back around. So I'm back at the top where I want to be. Okay. I know. Okay, so here we are. If you just wanted to select that, that's fine. But anyway, here we are. And I'm going to type in my M mult equation. Okay. So equals M mult for matrix multiply. Then I come over here and grab my this is important. I'm going to grab the intercept too. So I want that intercept column because it's got to multiply by the intercept row in my relationship matrix. So that's why we need those ones. That's what we're using to pull in the intercept. And then Control Shift down. So I've got the whole block. I've got the whole block with no labels. Okay? Then I hit comma. Once I hit the comma, then I can, go back to the top with my scrolly wheel or, using this scroll bar over here on the right. Okay? And then I go put the cursor after that comma, and then I go and get my relationship matrix. And this one I want to anchor. And I'm going to close the parenthesis and hit Control, Shift, Enter. And I get all of my molar volumes. Yeah. Okay. I wish I could make that formula bigger, but up here we have an M mult. The blue is my structure matrix. The red is my property matrix. and we've got to accelerate here for a little bit. And I hit Control Shift Enter, and I get the full thing. Let's quickly do what I call a performance plot. Okay, but first let's make sure everybody gets to this point. Yeah, so 1 times the intercept plus the carbon times that plus the hydrogen times that. And so it's a useful tool. It's only because we're using matrix math. Okay. Yeah, that's right. The coefficient of the intercept is 1. Yes?
What scenarios would we have to be in to use Control Shift Enter versus using just like dragging it down? I tried doing the molar mass one, and I did everything except for Control Shift Enter, and it didn't calculate it correctly.
It didn't calculate correctly?
No, but whenever I did press Control Shift Enter, it did.
I'm not sure. I'd have to look at that specific case that you're talking about. But I want to move on because we've got to do the performance plot next. But I need everybody to get to this point. Okay, does everybody have this point where they have the molar volumes? I don't think so because of the looks on your faces. Okay. Are you having trouble? Okay. Control Shift Enter. You may just use page down, shift page down to get down there if you want. That'll be easier than doing that craziness that I did. So let me enter it again if you want to follow along. Okay, I'm going to delete everything. Okay, so here let's do it to get a more normal way. It's using shift and page down. Okay, I use shift, page down, and a couple of the down arrows. And I hit equals mmult. And then I go over and get my structure matrix. To the right arrow, Control Shift down, comma. And then come up to the top. Grab the structure, the relationship matrix, close parenthesis, Control Shift Enter. Okay, and did you get the molar volumes? Okay, good. Nethmini, Jamari? Oh no, so work with her. Is yours working? Okay. Do you have it yet? Christian, you have it? Okay. Madri? Yeah. Okay, all right. Okay, so we have an R squared for this, but I like to use what's called a performance plot. We have literature values, and we have our modeled values. In a perfect world, they're the same number, right? So if we plot our values, QSPR values, versus literature values, we ought to have a slope of 1. And an R squared of 1, right? We shouldn't have any scatter in the data. So let's take this VM column. Okay, y'all ready for some more hocus pocus? Let me show you an easier way to plot this. Pick any 2 columns to plot, okay? So here we are. Let's pick these 2 columns to plot. Okay, 2 adjacent columns. Make a scatter plot. Okay, so come up here, insert, scatter plot, just dots. Okay, it's ugly. It's density versus molar mass. Okay. All right, I'm going to drag that up to the top. I hate dragging, but I don't want to confuse you with another hotkey. Okay, so we just plotted 2 random columns in our data set. The reason I wanted to just plot 2 columns because I wanted to plot 2 adjacent columns. See, our VM is not adjacent to anything, so it's kind of a pain to plot columns that are not adjacent. Okay, so what we have now is we have this plot, and we're not really interested in density versus molar mass, but we can click one of the data points. Okay, so you've got your plot, click the data, and then you can drag these columns around to plot what you want to plot. So I'm going to drag this y value over here,
Oh,
and I'm going to drag the label over here,
so you have to like.
and then I'm going to drag the x-axis over to my literature values, the literature VM.
Are you like holding control or something?
I'm just with the left mouse button clicking and dragging. So I get right on the edge. Watch here. See, when I get close to the edge, how the purple gets bolder? When the purple turns bold, you can grab it. You can put it anywhere you want. And so that's the fastest way to graph two non-adjacent columns. Do you see my issue? I've seen people plot things that, I mean, the long, tedious nature of plotting things drives me crazy. And so I just plot two adjacent columns and then drag the data set around where I want. Look at that. That's beautiful. This is our QSPR on the y-axis plotted versus our literature values. And so I'm going to give this axis titles, and we call it QSPR. Oops. For the y-axis. And then for the x-axis, I'm going to click that title and type in lit. So we did pretty well. I mean, there's some noise in there, but still, you know.
Yeah, it's like 97 squares.
Yeah, so let's go ahead and put a trend line on this. Add trend line. And then I'm going to do the little arrow here and get more information on more options on my trend line. Okay, everybody follow along here. You see I've added a trend line. I'm going to go to more options. And then down here at the bottom, I want display equation, display r squared, and set intercept to 0.
Am I saying just y equals x? I guess just because they're running.
Because it's perfect. Yeah. So,
I have the same r squared, or we should have the same r squared. Yeah.
but yours is rounded to just y equals x? That's bizarre, yeah. So that is a pretty good performance. In other words, our on average, our QSPR is only off by 0.4%. So I can take my QSPR value and I know it's 99% the literature value. 99.6% the literature value. That's amazing. So I have uncertainties associated with each one of the coefficients, carbon, hydrogen, nitrogen, and oxygen. But overall, my QSPR is, again, on average, 99% accurate. So this on plot is a really useful plot. Yes, any individual value, it may be off, fair percent. But in this whole data set, I've matched literature 99%. Because if I plot QSPR versus literature, the slope is 99.57%. Okay, that's a little different claim than the r squared value. The r squared is what percentage of the scatter is captured by your model. Okay, the slope value is your accuracy. How accurate is my model? You see the two different ones? The r squared is precision, and the slope is accuracy. So it's accurate and fairly precise. Okay. Any comments, any clarifications that you need on this? Do you see how powerful this is? I can do this now backwards. I can tell you the molar volume and the molar mass, and now you can calculate the density. So with this simple, you tell me the molar mass of something, and I can tell you if it floats or not. Right? That's pretty cool. So a little David Letterman sketch. This is dating me, but he had a sketch. Will it float? Okay. Yeah. Stupid human tricks. But, yeah. So this is a pretty nice setup. Well, we were playing around with this idea, and I thought, what about enthalpy of combustion? It was in thermodynamics, in the thermodynamics course, and I thought, let's see if we could calculate or predict the fuels, the heat value you get out of fuels for combustion. And so in the paper, we will run out of time if we try to go through this in detail, but these numbers can be gathered from the CRC. This is where I got all of these delta H of formation values. And you can turn the delta H of formation into combustion enthalpy using this equation here. So if we have the delta H of formation for these compounds, we have the delta H of formation for CO2 and for water and for NO, we can compute the combustion enthalpy. And so that's what I've done in this spreadsheet to give you this column right here. I've got the literature values for delta H of formation. I've calculated the heat of combustion. So go to the paper that you've got for learning the differences between these columns and how that was implemented. And then I just changed the sign to make it a volume of positive value for the lower heating value. Now it's the lower heating value because water's still a gas. The upper heating value is to capture the heat of condensation of water to get it back down to room temperature. And so this is what you're going to capture in a combustion engine because water's still a gas when it leaves the tailpipe. If we held it in the piston until water condensed, we'd get a little more heat out. But it's not practical. We can't really run a combustion engine that way. So we don't get all of the heat out of a combustion situation that we could get if we could get the condensation heat out of water. That's why they call it latent heat of condensation or latent heat of vaporization. So these are the lower heating values, and we're going to do a regression for this. Let's see, if you tell me how many carbons it has, how many hydrogens, and so on, can I tell you how much heat it will produce as a fuel? So let's do another regression. So data analysis, regression. So here's some more practice. We're going to delete those values there, and I'm going to grab this LHV column. I'm going to get the label, Control Shift down arrow. Those are my Y values. Control Shift down arrow. So if you don't see the dotted, box around that whole column, then you've got it wrong. I'm going to change my regression to LHV1. I'm calling them 1 and 2 in case we need to do the intercept or get rid of the intercept. But in this case, we don't. My intercept p-value is 0.003. So that's less than 0.05. So I like that. So I'm going to keep the intercept.
That's even better.
Yeah, and look at the R squared value. It's even better than the molar volume, 0.996. Here are my coefficients. So this is my relationship matrix. This will convert the molecular formula into how much heat I can get out of that in combustion. So we'll collect or control copy that set of values. Be sure to get the intercept as well. Everybody got that? You copy those 5 values. Do you have the regression? Okay. Yeah, you can clean things up, yeah. Okay, so I've got the regression. I'm going to Control C or copy those 5, the relationship matrix, go back to the top of my spreadsheet, and I'm going to paste that into the LHV relationship matrix area. Control V. So there's my LHV relationship matrix. And then right here for the QSPR, for the LHV, I've got to select all of those columns again. I'm going to use my trick. I'm going to go over here, Control down, right, Control Shift up, Shift down, Tab. Let me do that again just for you at home. So I'm going here's where I want to go. Left, Control down, right, Control Shift up, let go of the Control button, hold the Shift button and go down arrow 1 time, and then hit Tab. It's like a dance move, okay? I've had easier line dances than this. Okay, so left, left, control down, right, right, control shift up, shift down arrow once, no control. Okay, tab. Crazy, I know,
Oh my God.
but I like that better than page down, page down, page down, page down, page down. I don't know. Maybe you're a page down person. I'm not. Okay, so there's gonna be two types of people. Okay, equals mult. Open, and then go get my carbon, hydrogen. I've got to get the intercept column too, though. So I'm going to come over here and get the ones. And I'm holding shift down, right arrow, shift down, and then control shift down. So, comma. And then I go get my relationship matrix for the LHV, the lower heating value. I'm going to try it without anchoring it, see what happens. Control shift enter. Okay, it works. The anchoring is really if you're just going to like copy that other places in the spreadsheet. Okay, so here are my values. I mean, I could compare them. This is 1229 and that's 1083. I mean, you know, they're the same order of magnitude, but let's do our performance plot. Okay. Well, let's go get our performance plot that we just made. And this is the beauty of control drag. I'm going to grab this guy and I'm going to control drag. I love that. Control drag. Why is it not working for me? Control drag. Okay, control drag. There we go. I started dragging and then hit control. Okay. All right, so then I'm going to scoot this over to where I can see my LHV column.
Oh, I didn't catch that. You can hit it by control drag.
Yes.
Oh, wow.
Yeah, okay. So you got to click the data, not the trend line. So this can be tricky. Click the data, and when you click the data, you'll see that QSPR light up. See right here, I've got the data now. If I click the trend line, I don't have anything. So I click the data. Okay. All right, I click the data, and then I drag that over. Ooh, I've got two trend lines there. That's weird. I'm going to delete one of those. Oops, I deleted the one with the equation. Oh well. And then so I've got the Y over on my QSPR, but I've got to move the lit. So move the literature over to the LHV column. Okay, look what it's doing. Pay attention to this one. I'm trying to drag this to the right, and it won't move. It won't move to the right. It's because I have the whole chart selected and not the data. You've got to click the data if you want to change the actual axes that are being plotted. So see, now that I've clicked the data, I can move the x-axis. Okay, so that's my LHV performance plot.
Oh, yeah.
And so I click that trend line. Over here, my trend line options. I've got this is like the coloring of the trend line. I come over here and click this little deal here, and I get the different options for the trend line. I'm going to set the intercept to 0, display the equation, display R squared. So this one is even more accurate and more precise. It's amazing. Yeah. Now, this one is very clear. I know what the differences are here because we're getting the heating value from literature, and we're modeling the heating value based on CHN and O. Now, ethanol and dimethyl ether had the same molecular formula, but they have slightly different heats of combustion. Because one has got an OH bond, the other has two OC bonds. So you see that's going to be slightly different energetics. And so we know what the spread is in this heating value. It's based upon different functional groups, but they may have the same molecular formula. But we've got such a spread in the data because this goes up to C70. And so because we have such a huge variety of types of molecules, we've got a wide range for our regression, and that's why we are able to get such a good R squared value. But if we had a really small data set where we only got down into the like ethanol and dimethyl ether and so on, we wouldn't get quite as good a fit because our training set would be tiny and these small effects would confuse the data. So hopefully this, I guess we've got the 1 minute left, for let's sum it up. Hopefully this gets across to you the power of quantitative structure property relationships. Meaning you have some kind of structural parameter and you've got some kind of property and you can use statistics to join the two. This is just statistics. So I could have the property be the lowering blood pressure, and I could have all of the molecules to this point that lower your blood pressure, and I could look at all the different properties. I could look at their molecular formula. Probably not going to give a good R-squared value. But what if there was some sort of functional group, an aromatic ring with a methyl group on it, that the good drugs had that the bad drugs didn't have? I could take these structural parameters and count up how many aromatic rings does it have, how many methyl groups does it have, how many ketones does it have, and make those my structural properties and my structural parameters, and my property be lowering blood pressure, and then I could get a relationship matrix. So what? Well, what that means is I could take an unknown molecule, run it through the same matrix, and gauge its potential for lowering blood pressure. And that's why pharmaceutical companies really love these statistical relationships. This is how they decide what to invest money in on the next trial. The next lab, research is saying, okay, we have this QSPR, and in those cases it'd be activity, lowering blood pressures and activity, so it'd be QSAR, quantitative structure activity relationship. And they would use the statistics to decide what are the promising molecules that we need to look at next. So there really doesn't have to be anything but a statistical relationship between the structure and the property or the activity. Notice we're not saying mode of action here. We're just saying that it's a statistical relationship. Okay, so that's a good place to end.